Hello, thank you for watching this presentation. We will be walking you through our work for the CAC Fighter 1 course assessment. The main focus of the assessment being the ASL algorithm. We explore this application through a problem scenario which involved implementing A-star and conducting research on different scenarios and the variations of the algorithm. These are our group members, Renard Itawaru, Ricardo Narain, Shivish Mohammed, and myself, Marcus Mangru. Before we get into the fine details, let's look at our problem description. And in our problem scenario or description, we have a game Mark, who is a game developer. And Mark wishes to create a game which is similar to Fire Emblem. And for context, Fire Emblem is a tactical RPG where the characters battle on a grid-based map. And in this game, you control your characters and you go against enemies and you fight and so on. And you fight, defend, and so on. And the problem comes up in this case is while you are able to move your characters, click on them, move them, and so on, how are the enemies able to do the exact same? And for this, we look into pathfinding. And when Mark reached that point, he wanted to make use of the ACE algorithm, which and to get more what A-star is, A-star is a fast and powerful pathfinding algorithm. So it's applicable in this case. And it's widely used in games, robotics, and even navigation system. And it's known for finding the shortest path quickly while balancing efficiency and accuracy. So Mark was planning to use this algorithm for his enemy AI so he can navigate the grid and move towards the player. So to better show what was happening or what was going on, the scenario, let's look at this example of what it's like. So this will be the environment to be like. So we have a grid-based system, we have a grid here. And then the first thing, let's look at our key. So the first thing we can see, we have this enemy character, which is in the black here. So we have this character here. And these are the ones who will be traversing the map. And secondly, we have our playable characters. This is the goal that this enemy character is trying to get to, is this playable character. And we have trees. We see a different type of trees, but we have trees and we have scrubs, and these are obstacles. And if you were to look here, you can see non-traversable, non-traversable, non-traversable. This is referring to them being. This is referring to the enemy character cannot traverse these spots. So these are the obstacles in the way. So they cannot go. They can get to the player. Goes to get to the player, but they can't go through them. Same thing with trees and so on. For example, so they can move here, 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 and so on and here and they get here. But if they try to come here and go straight to the trees or straight to the shrub, that's an invalid move. So they have to try to get to that path with the most efficient way possible. So, and that's it for this is a very surface level explanation of our scenario. So and then to have a better idea what's going on, I'll be sending you off to our next crew member, which will be going through a demonstration.
Demonstration. So to run our code for one agent, we simply need to ensure that adversarial is false, and if we did want a random seed, we can put -1, and then we run python main.py, and this here will show an agent. In this case, the agent is set to follow the greedy strategy, where it will only consider the immediately next node in its decisions. To randomize, we can use this randomize function. Alternatively, as was just seen, when it finds its goal, it will simply reset the map, and it will run until simulation count has reached the number that it's set as, which in this case was simulation count equal 3. So that's not included in the times I click randomize. Okay, so to run the adversarial situation, we're going to change this to true, but in addition to that, we're going to set the seed to 100 to perfectly replicate the maps generated in the experiment. And then we can run python main.py. Additionally, we can also click show paths. An interesting point of note is that the greedy strategy agent 2 will keep a history of paths, while the complete strategy option agent 1 will show you the future path because it's already calculated its path. and it just needs to follow it. Meanwhile, the greedy strategy is just making it up as it's go. And with that, you will see the experiment completed. So that was 3, and with that, some results are outputted. The times are not accurate, so that's really just for display. For things like times and accurately measuring the times, we would use main.display.py, which will simply set show equal false, which means it will not show the GUI, which will be a big factor for influence in the runtimes. And we just run python main.display, and you will see the times are significantly slower. Another point of note, to configure the individual agents as well as the adversarial agents, you can go to simulation.py, and the configuration of the strategies is done right somewhere here. So here you can configure the strategies. If it's adversarial, you configure the 2 agents here, and if it's non-adversarial, which it means it's just the 1 agent, you do it here. And with that, that concludes the demonstration.
I will now walk you through the key findings from our experiment comparing the complete A-star and greedy approaches. So first up, we found that the complete A-star approach consistently produced more optimal solutions, and this was true when tested alone and adversarially. And optimal solutions in this case would refer to the fact that it was able to identify paths to the goal with the lowest total path cost. The greedy approach, on the other hand, excelled in speed, reaching the goal faster than the complete approach in a higher percentage of trials. Despite these differences, the overall runtimes of both approaches were fairly similar, which suggests that while the complete approach spends more time calculating the optimal path, and the greedy approach makes quicker but potentially suboptimal decisions, the strategies balance out in terms of total execution time and total system resources used. To get a better understanding of the agent's behavior, and just to verify our findings, we increased our testing from the initial 3 runs to 1,000 runs and discovered that the agents tie in over half the cases, and this held true whether we used linear or Manhattan heuristics, suggesting that while each approach has its distinct advantages, the overall performance levels are more comparable than we initially expected.
Continuing the experiment results, the following data was collected across 2 sets of adversarial runs. In the first run, agents 1 and 2 were tested, while in the second run, agents 3 and 4 were tested. Across all test simulations, the time taken was relatively consistent, regardless of whatever heuristic function and strategy was used by the agent. However, agents using the complete A-star search generally took slightly longer than those using the greedy search method, which checks out due to it having to compute more paths. Examining the path costs for each agent shows that agents employing the complete A-star search consistently chose paths with lower costs and often identified the most optimal path. In contrast, the greedy approach tended to select paths with higher costs. In the adversarial setting, where the main goal is to reach the objective before the other agent, path length becomes a critical parameter. The results show that the greedy approach performs slightly better in terms of path length compared to complete A-star. Consequently, the greedy approach succeeded in winning 2 of the 3 mazes and tied in the final. Now, to get a better understanding of the effects of the different heuristic functions, we expanded the sample size from 3 to 1,000 mazes. In the first set of 1,000 runs, Agent 1 used the complete A-star approach, while Agent 2 used the greedy approach. Both agents also used the linear heuristic function. We can see that, as expected, the agent with the complete A-star approach had a noticeably lower path cost, about 20% less. The runtimes, however, averaged out to be about the same, with the complete A-star actually slightly beating out the other strategy. Also, we can see that our greedy agent was able to win almost 4 times as much, but it was also unable to find a solution 2.5 times as much. Now, we ran another set of 1,000 runs, where Agent 1 again used the complete A-star strategy, and Agent 2 used the more greedy approach. However, this time, the agents used the Manhattan heuristic function. Once again, we noticed that the complete A-star had a much smaller plat cost, about 25% less, and the runtimes were about the same. But the win rate of the greedy approach was 3 times as higher than that of the complete A-star approach, with the trade-off of being unable to find a solution or getting stuck about 3 times as much.
So what do these findings mean for Mark's game development? Since we discovered that both the complete and greedy approaches often achieve similar results, Mark could strategically use this to create more diverse and engaging enemy behaviors. For instance, he could use the 8-star approach for more tactical enemies that need to navigate hazardous terrain or complex battlefield layouts. So for example, enemies that need to preserve their health while advancing. And the greedy approach could be perfect for creating more aggressive enemies that rush straight at the player. Additionally, the similar runtime performance means that he won't have to worry about one approach impacting the game performance more than the other, and the high tie rate suggests that both approaches will create competent enemy AI that can effectively challenge players, just with different behaviors. This brings me to the end of our presentation. Thanks for listening.